Chapter 6, number 15. A certain spring has a force constant K. A, if two such identical springs are connected in parallel to each other as shown in part A of the figure, does the resulting double spring have an effective force constant that is greater than, less than, or equal to K? And explain. If two of the original springs are connected as shown in part B, does the resulting double spring have an effective force constant that is greater than, less than, or equal to K? And again, explain. So let's talk about part A. What we're really talking about is if we replaced the two springs with one new spring, what would the constant of the new spring have to be to produce the same motion, which means to exert the same force on the block. So let's talk about the forces on the block. If we move the springs over a little bit, then they will each exert a force back, which we might call like F spring 1. That's terrible. Just call it F1 for now. And then the other guy will exert F2. And in both cases, F1 will equal F2 will equal K times X, whatever the distance we moved the box over. So if we moved it over some small distance, or really here some huge distance, then each guy produces that. So the net force on the box is F1 plus F2. All right, so the net force on this box is F1 plus F2, which is Kx plus Kx, which is 2Kx. And we want that to equal some new spring exerting some new amount, which I'm going to call F equivalent. And F equivalent is going to be some new spring constant times X, where I'm using capital K for the new spring constant. So in that case, the sum of the forces is F equivalent, which is capital K times X. We can put those together to say that Kx plus Kx is capital Kx. The x's are all the same, so I can factor them out. I have 2Kx is capital Kx, or capital K has to be 2K. So the new spring constant is twice the original spring constant, so clearly, therefore, greater than, because it's exactly twice as much. These are called parallel springs, and that's sort of a useful thing to know, that if you add two identical springs in parallel, they get twice as strong. Part B is actually a little bit more interesting. In part B, we move the box over a little bit like this, and that means that the left spring has gotten a little bit larger by X, but the right spring has gotten a little bit shorter by X. And at first you're like, well, isn't this going to cancel out? But in fact, if you think about it, the stretch spring pulls the box to the left. And the compressed spring also pushes the box to the left. So these two guys are actually adding the same way. So if I draw a free body diagram, I would have F1, the guy on the left, pushing that way, or pulling that way, and F2 pushing that way. And in both cases, the magnitude is still K times the distance. And we want to replace that with one spring, which is pulling over with some equivalent force, which we'll assume we'll say we attach it on the left. It doesn't really matter, but we put it on the left. And so in that case, we would have that the equivalent spring is some constant, capital K times X. And we are left with the sum of the forces has to be the same in both cases for this to work out. So we would have Kx plus Kx is the same as capital Kx, or again, capital Kx is twice K. And again, the effective spring constant is greater. So it really didn't matter whether the springs were both attached on the same side or on opposite sides, because by flipping the side, we also flip the direction. And so it ended up being the same kind of force.